is we're going to be talking about enthalpy, which is symbolized with the letter H, which may not seem to make a lot of sense. But enthalpy is the total internal energy of a system, both potential and kinetic. The potential based off of moving things apart or together, and kinetic based off of speed or motion. And it's very difficult to measure the absolute value of enthalpy, but it's easy to measure the enthalpy changes. For instance, it's very difficult to measure the volume of the ocean, but if you were to grab a 1 gallon jug of water and go pour it into the ocean, you know that whatever the volume of the ocean was, it's now increased by a gallon because you just poured it in. So we just kind of use calorimetry to measure enthalpy changes. Now, at constant pressure, the change in enthalpy, which is abbreviated with delta H, equals the change in thermal energy, Q, also known as heat, of the system. And all of our experiments will be done at constant pressure. We are not going to be heating or cooling sealed up vessels. We're going to be at constant pressure. So for our purposes, as long as the pressure doesn't change, which it won't in this class, delta H essentially equals Q, which is why the H for enthalpy kind of makes sense because it basically means heat. And so delta H equals the heat of your products minus, or the enthalpy of your products minus the enthalpy of your reactants. Next, we're going to look at something called Hess's law, which is ultimately going to help us with our lab that we're going to be analyzing on Wednesday. And if you were absent, you have not done the lab yet, you need to email me and schedule a time to do that lab on Wednesday. So Hess's law, the change in enthalpy for a reaction is the same whether it takes place in one step or it takes place in multiple steps. If you reverse a reaction, then you change the sign of delta H. And the magnitude of delta H is proportional to the quantities of the reactants and products. If the coefficients are multiplied by an integer, so is delta H. Because delta H is measured in typically kilojoules per mole. And if you double the number of moles, you double the amount of heat. For instance, if you know the amount of heat produced when 1 mole of wood combusts in a fire, if you double the amount of wood, you double the amount of heat. If you cut the amount of wood in half, you cut the amount of heat in half. It's like common sense. So now we're going to analyze something called standard enthalpy of formation. All right, so the standard enthalpy of formation, delta HF with this little degree sign, is the enthalpy change for the formation of 1 mole of a compound from its elements with all of their substances in their standard states at 25 degrees Celsius. That's a lot right there. So let's kind of break this down. The little degree symbol up here means standard conditions, which if we're a gas, that means the pressure is at 1 atmosphere. If we're dissolved in solution, our molarity is 1 molar. And we're in whatever state of matter that's stable at 25 degrees Celsius. If we're talking about water, that would be a liquid state because liquid water is stable at 25 degrees Celsius. If we're talking about copper, that would be the solid state. If we're talking about aluminum, that would be the solid state. Oxygen, that would be the gaseous state. Now, for an element that is in its standard state at 25 degrees Celsius, the standard enthalpy of formation is defined to be 0. That's what that triple equal sign means. It is by definition equal to 0. In other words, for an element in its standard state under standard conditions, its standard enthalpy of formation is defined as 0. Because since we're measuring enthalpy changes, we have to pick a baseline that everybody agrees on. So they've just taken all the elements on the periodic table and said their standard enthalpies of formation are 0. If you're talking about oxygen gas, O2 is how oxygen gas is stable at 25 degrees Celsius. Its standard enthalpy of formation is 0. H2, it's 0. Solid aluminum, standard enthalpy of formation at 25 degrees Celsius is 0. Now, in equation form, Hess's law looks kind of like this. The change in enthalpy equals So Hess's law in equation form looks like this. It says the change in enthalpy equals the sum of the standard enthalpy of formation of the products minus the sum of the standard enthalpies of formations of the reactants. So it's products minus reactants is delta H. And that's important to note. If you somehow manage to forget that on your reference tables, it's right here. It says that standard enthalpy of formation equals the sum of the standard enthalpy of formation of the products minus the sum of the standard enthalpies of formation of the reactant. All right, so let's take a look at an actual AP exam problem. So we have a reaction here. And it says a student was assigned the task of determining the enthalpy change for the reaction between solid magnesium oxide and aqueous hydrochloric acid, represented by the net ionic equation above. As you'll notice, the chlorides are not shown because they're spectator ions. Student uses a polystyrene cup calorimeter and performs 4 trials. Data from each trial are shown in the table below. What is the limiting reactant in all 4 trials, HCl or MgO? Justify your answer. Now, you'll notice that even when we when we double the amount of magnesium oxide, we kind of double the temperature, it looks like. So that would mean that magnesium oxide is our limiting reactant because it's the one that affects the temperature change in the reaction. Whereas if HCl were the limiting reactant, then adding more magnesium oxide would not have caused a greater temperature change. Right? So then let's take a look at this next part. It says the data in one of these trials is inconsistent. So draw a line through it and see how we identified them. So in trial 1, the change in temperature was 1 degree Celsius. In trial 2, the change in temperature was 4.1 degrees Celsius. In trial 3, our change in temperature was 2.1 degrees Celsius, and here it was 4 degrees Celsius. So the data that looks inconsistent appears to be trial 1. So we're going to draw a line through trial 1 because it looks like typically for half a gram of magnesium oxide, you get a 4 degree temperature change. So for a quarter of a gram, you should get a 2 degree temperature change. And we only got a 1 degree temperature change. So that would be the one that is inconsistent with the results. Now the problem wants us to calculate the magnitude of Q for one of these other trials. And it says, use the data from one of the other 3 trials. Assume the calorimeter has a negligible heat capacity and the specific heat of the contents is 4.18 joules per gram degree Celsius, and the density of HCl is 1 gram per milliliter. So if we're going to do that, what we need to do, let's just take trial number 4, where the change in temperature happened to be, we said earlier, was 4 degrees Celsius. So Q equals, our mass is going to be 100 plus 0.5, because we've got 0.5 grams of magnesium oxide. So it's going to be 100.5 grams times the specific heat, 4.18, times our change in temperature. And so if we multiply that out, we get 1,680 joules. Then it asks us to determine the value of delta H for the reaction between magnesium oxide and HCl in units of kilojoules per mole. Now the reaction was 1 magnesium oxide plus 2 H pluses. So what we need to do to get this in kilojoules per mole, we said already our limiting reactant was magnesium oxide. So let's take our magnesium oxide. We have 0.5 grams of magnesium oxide, and we need to convert those grams into moles. So we take the mass of magnesium plus the mass of oxygen, and we get 40.31. And so that's 0.012 moles. So now we take the 1680 divided by 0.012, and we get 140,000 joules per mole, or 140 kilojoules per mole. So enthalpies of formation for the substances involved in the reaction are shown in the table below. Using the information in the table to determine the accepted value of delta H for the reaction between MgO and HCl. So we're going to use Hess's law, which says that the delta H for the reaction equals the standard enthalpies of formation of the products minus the reactants. So our products are Mg plus 2, which is negative 467 kilojoules, plus H2O, which is negative 286, minus our reactants. So MgO, negative 602, plus H2O, H plus, which is 2 times 0. Now we would do 2 times it because it had a coefficient of 2 in the reaction. And so we put this into our calculator. And we get negative 151 kilojoules per mole. All right. Now, what does it mean that this value is negative here? Well, it means that the reaction has released heat. And by the way, so we're looking back at part D for that reaction. Since that reaction released heat, for the delta H of the reaction, we should make that sign negative because it released heat into the surroundings. The thermometer that measured that temperature change was part of the surroundings. And then it says the accepted and experimental values do not agree. If the calorimeter leaked heat energy into the environment, would that help account for the discrepancy between the values? Well, ultimately, if it leaked heat into the environment, then that would cause the temperature to not have increased as much in that experiment. And so that would definitely account for the discrepancy. It would make the delta T not big enough in the reaction. And therefore, if we go back to our calculation with Q equals MC delta T, Q would be too small, so this whole thing would be too small. And that would be our answer.